So now we're going to look at a different way of using classifiers and regression. That's called lazy learning. And we're going to start by looking at what is this concept, and then looking at a classical example of lazy learning, which is the k-nearest neighbors classifier, how we can use that for regression too, so a k-nearest neighbor used in regression. And then we're going to expand this for kernel regression and kernel density estimation. Kernel density estimation is actually an unsupervised learning technique, but you're going to use this on the first assignment, and it fits well with this part of kernel regression, so it's easy to cover it now. But first, the idea of lazy learning. What we saw so far is that we have some hypothesis class that we represent with a model, typically with some parameters, a polynomial, the logistic regression, something like that. And then we use the training data to fit those parameters until we have a hypothesis. So this is the most work we have, computational work, fitting the parameter to our training data. After we fit the parameter, we can discard everything else. We don't need to store our training data or nothing like that. All we need is the parameter for the final hypothesis, the parameters, and then we can use that to classify or predict new values. So this is what we saw so far. These are examples of eager learning. We are doing all the work first and try to get everything as tidy as possible at the beginning. So we represent a hypothesis class with a model. We train the model on the data. Then we don't need the training data anymore, because now we're only going to classify the new points. And we answer each question based on the model, on the hypothesis that we fit, and on that adjusted model. With lazy learning, we don't do anything in the beginning. So we just store the data, and we go take a break, go to the beach, or something like that. So there is no actual learning here. We do have a hypothesis class, but we are not representing the hypothesis class explicitly. So we are not fitting parameters or anything like that. What we do is, when somebody asks a question, we have a way of looking at our data and trying to predict what is the best answer. So let's see that with the k-nearest neighbors classifier. The idea here is that in the first stage we have a training set. We simply store the training set. And now every time someone asks us a question to predict, say, the class of a new point, we are going to look at the closest k examples in our training set. We see what is the majority class in those closest k examples, and that is the answer that we give. So there is implicitly here a hypothesis class, but there is no actual model. We are not trying to describe the hypothesis class with some parameterized model. We are not trying to learn the parameters. We are just storing everything and answering the question when the question comes. So there is no model, there is no actual training, and we answer based on the stored data. So let's see what happens if we use k equal 1. So this would be the k nearest neighbors with k equal 1. We have this data set stored, and what happens when someone asks about what would be the class of a point here or here or here, what we're going to do is we're going to look at the nearest point in our data set, the set of points that we know the class for, and we make our prediction based on the class of that point. So when we have k equal 1, we have this Voronoi tessellation, assuming that we are using Euclidean distance. That is basically this partition of all our surface, or all possible points, that is divided by these lines that are between each pair of points, the closest neighbors. So if points that are over here are closer to this point, and they are classified or predicted to be blue, points that are over here are closer to this point and predicted to be red, and there is a line here that is perpendicular to the line between these two. And then we reach some point where other 2 points are the closest neighbors, and we have all these lines separating those parts of the tessellation. If we use higher values of k, we get more complex tessellations, but the idea is always the same. We have all these lines, straight lines, dividing the region. So in this case, it's the k nearest neighbors with 3 points. So for here, for example, although we are close to one blue point, we are also close to 2 red points. So since the closest three neighbors of points in this region, it has two red and one blue, this part here is predicted to be red. When we reach this part, this side, then we predict it to be blue. Note that it's usual to use k values that are odd, not even, because if you use even values, you can have a tie, and then it's harder to decide what to do in those cases. So usually with k nearest neighbors, with two classes, we use k values that are odd. In any case, regardless of what what the number of k is, the discriminant is always piecewise linear. It's not a single straight line, but it's a set of straight lines. It may be more intricate with a larger number of line segments, but it is always linear in each segment. Because of the way, given at least this definition of distance, using Euclidean distance, because of the way we partition this space. So basically, we can obtain a dividing line that is a set of line segments using Euclidean distance that we can adjust depending on the value of k. So if we use a very low value of k, for instance a k of 1, we have a very intricate line because at each point we are deciding based on the single example that is closer to each point. If we increase the number, the neighborhood, say for example with a k of 25 here, we are assigning the values for each point based on the 25 nearest neighbors. So we are looking at a broader region for each point, and we have something that is a different frontier here. So you can see that usually we'll have to adjust the value of k depending on our data, but we already know how to do these sort of things. We can do cross-validation, and we can select the best value of k depending on the cross-validation error. But in order to do this, in order to find the k nearest neighbors, we need to sort everything by distance and then choose the ones that are closest. So for this classifier, we need a measure of distance. In all these examples I showed, I used Euclidean distance, which is basically Minkowski distance, or p norm, using p equal to 2. But this is a more general expression for distance measures, which is the p root of the sum of the modulo of the difference between the different feature values, each one raised to p. So if you use p equal 2, this is Euclidean distance. This is the sum of the square differences between the coordinates, and then you do the square root of that. This is simply the Euclidean distance you are used to in geometry. If you use a p value of 1, this is Manhattan distance. You are measuring in the horizontal and vertical lines because you are just summing the modulus of the difference to compute the distance. But you can use different values of p. This is useful when you have continuous values for the features. Sometimes you have categorical features. We did not see that examples of that before, but in k nearest neighbors can also be used when you have categorical features. So you can have things like sex, or the district where a person lives, or the profession, or something like that. So if you have these sorts of features, you don't have actually continuous numerical values for computing the difference. So one distance measure that you can use is Hamming distance. This is a sum of all the features that are different. So two examples are more different depending on the number of features they have that are not the same. If all the features are the same, the distance is 0. If they are all different, then the distance is the dimension of the features that you have. But in any case, you can have different distance measures, and you can use depending on the work that you're doing or the data that you have. And these different distance measures will have an impact on your classifier. For example, this would be p norm distance with p equal 2, the Euclidean distance, Minkowski distance with p equal 2. But if you use p equal 1, you have this frontier like this. This is Manhattan distance. If you use a p equals 0.7, for example, you get something that is very weird. So depending on the distance measure that you're using, this can give you completely different results. Okay? So you should take care to adjust the distance measure to the type of data that you have. Now, how we can do this in practice? This is to show a simple implementation of a k-nearest neighbor classifier. We can compute the distance. In this case, this is more to illustrate some other tricks that you can use for functions in Python. In this case, we have a function that receives the values for our points to compute the distance. So this large X is a matrix of all the data sets, of all the data points that we have. The small x is one point for which we want to measure all the distance. And then we have this p-value for the Minkowski distance here that tells us what kind of distance measure we are using, and it has a default value of 2, which means that we don't need to give that argument when we are calling the function, because if we omit it, it's used with a value of 2. So this is the square difference in the case of the p-value of 2, but in general it will be the p root of the difference module raised to p. We are going to subtract from our matrix with n data points, we are going to subtract this single data point. Because the NumPy matrices do this broadcasting of the operation, we are actually subtracting from each point in the matrix. And then we're going to compute the absolute value of each of these differences, and we're going to raise them all to all these differences to the power of p. And now we're going to sum and raise everything to 1 over p. So we are doing this computation, and then we are doing this root here. And finally, we return the distance. So this way, yeah.
How does p affect the distribution? How does p affect that image level?
Because these are, for example, with p equal 1, you are adding the differences in coordinates, the absolute differences in coordinates. So you are computing the distance. For instance, the distance between this point and this point is this value plus this value. If you use p equal 2, the distance between this point and this point is this length here. So depending on the different distance values, different distance formulas that you use, which point is closest will change. Because if you are aligned with this one, for example, here you are closer to this point than this one. But as you start rising up, then this changes abruptly because you are adding the difference between the y and the x coordinate. This does not happen here. It doesn't matter if you go up and down because you are using the Euclidean distance. You are counting the diagonals too.
A high value means closer.
Not necessarily, because since this is a power and then a root. For example, if you use p equals 0.7, you get something very strange. If you use a very high value, I'm not sure what will happen. But this is not something that is very intuitive because of this kind of operation that you're doing here. You're taking the absolute difference, raising to some power, adding everything, and then using the square root. How exactly this behaves, it's not that obvious to imagine. But you can experiment with this if you want. I can send the code, and then you can try different values. So this gives us the distances according to a Minkowski distance of using p, by default p equal 2. And now we're going to find the k nearest neighbor. So we have one point that we want to predict, all our data, this x matrix, and the number of points that we're going to consider in the neighborhood. So we're going to compute the distance to that particular point, from all our data to that particular point, and then we're going to use this argsort. Argsort gives us the indexes that would sort the array. So we obtain the indexes for sorting that array according to the distance, and so the indexes that we want, those that tell us which points are closest, are the first k indexes from argsort. And now we can classify classify one point. We know the x, we know the y, and we have this k value for the neighborhood. We get the k closest points in our data set to the point we want to classify, and then we return the most common class label of the points that are closer to the one we want to predict. So to get the most common class label, we use the mode function from SciPy Actually, the mode function gives us a tuple with the most common labels in order and the count of how many times those occur. So we only want the first of that tuple, the first list, which gives us the most common labels in order, and then we want the first of those labels. So that's why we have these two zeros here. But you don't need to memorize this, because what I would like you to retain is, first of all, you can implement a k-nearest neighbor classifier in Python with these three functions. So these two have 2 lines each, this one has 3 lines, and it's very easy to do that. And the other thing is just to get an idea that you have all these functions. If you want to find the most common value, you have that in the statistics module. If you want to find which indexes sort the array, you have a function for that, and so forth. So just look up the function or Google how you do something in Python, and you usually get a very simple recipe for those things. So you don't need to memorize how to use these functions. Just remember that you have them and you can use them. So to implement the k-nearest neighbor classifier, now we have a problem here when we are using distance function, because it raises the question of whether we should do pre-processing or not. Suppose that our features were things like life expectancy, gross domestic product, value of real estate a person has, and things like that. To measure distance using those kinds of values, we would probably have to standardize everything or do some kind of transformation, because it makes no sense to try to use years and income and things like that all as coordinates to measure distance without any scaling. However, if we are using actual distance values, for instance in meters, meters in altitude, meters to the north, meters to the west, and so forth, then we should not rescale things, because those are actual distances, and if we do some rescaling, we distort the distance values that we have. So, for pre-processing, when you're using distances between the points, such as in a k-nearest neighbors classifier, you must think about the data that you have, because it may not be appropriate to do some rescaling, or you may actually have to do some rescaling, otherwise it makes no sense. So try to do that without distorting the data, looking at what kind of information you have. In general, you'll probably have unrelated values, so it's a good idea to bring everything to the same scale. Sometimes that is not the case, so you need to take care with that. So let's see how we're going to do, how we're going to find the best k value for our classifier. We're going to load the data, we're going to do cross-validation and checking different values of k. We're going to use only odd values of k, because even values of k are ambiguous. And we're going to use this error measure as 1 minus the accuracy. So basically, the accuracy is the number of correctly classified examples divided by the total of examples, or the fraction of correctly classified examples. Our error will be the fraction of incorrectly classified examples. Note that we cannot use the test set to do this. If we want to have an unbiased estimate of the error of our final classifier, we cannot be using that value to select k. So once again, if you want to get that unbiased estimate, leave a set of points for the end just to get that estimate. But this is what we have in the validation error and the training error. The test error here is just for illustration, but we can compute it if we want to, but we cannot use them. So if we were to choose this value of k because it has the lowest test error, at that point the test error would no longer be unbiased, because given this sample we were deliberately picking the smallest one. So remember that the test error sometimes is above the true error, sometimes it falls below the true error. It's a random sample. If you choose deliberately the one that is smallest, you are most likely choosing one of those that fell below the true error, and now you're getting something that is probably underestimating the true error. So we are going to ignore the test error. We can plot it, but we are not going to use to choose everything, and we're going to choose the best value of k on the validation error. But the most interesting thing here is to look at this plot and see how different it is from the other plots we saw so far. So typically we found that we had, for example, with the polynomial regression, we had a part of overfitting where we had a very large training error and validation error, and then the training error would go down as we increase the power of the model, and the validation error would start eventually to go up with overfitting. But when we do k-nearest neighbors with a value of 1, the training error is always 0. Because unless we have points of two classes that are coincident, that are in exactly the same place, each point will always be the closest neighbor to itself. So when you're measuring the error on the training data, on the same data set that you have for the estimating, for predicting the class, if k equals 1, you're always looking at the same point that you're putting in. So there can be no errors in this case unless you have points of different classes that are coincident. So this is a typical pattern for k-nearest neighbors. In general, when k equals 1, you have a training error of 0. Then as you start increasing k, since you are looking at increasing neighborhoods, then you may predict a class for one point that is being influenced by other neighbors and change the class level. So you start increasing the error of the training set. However, for validation error, typically you have something like this, and then it may start increasing. So this is how we can select the best k, or also by cross-validation. So now we use k, the best k plus k equal 9. We have this frontier here, and now we use the test set to get the best error estimate. Note that at this point, while we are doing this, we were computing the averages of the different folds in cross-validation. So we were considering to have a training set, and the validation set was outside. Once we choose the best value of k, now we store all the training sets, and that will be what will determine the following prediction. So now we use the test set to get an unbiased estimate of the true error. There is a problem with these distance methods, and this is actually a bit difficult to imagine, which is called the curse of dimensionality. This is the effect of increasing dimensions in the way these regions are defined. So imagine that you have one thing in one dimension, and you consider that the frontier is 5% of the diameter. So, for example, 2.5% on each side. If you have the same thing in two dimensions, initially, in one dimension, this occupies only 5% of the total size of your region. But if you increase for two dimensions and you have a circle, then this ring of 5% width around the circle has actually more than 5% of the area of the circle, because it's in the widest part of the circle. When you increase to 3 dimensions, the problem gets worse. And so for this 5%, so in 2 dimensions it would occupy about 10%, in 3 dimensions 14%, and so forth. And as you increase dimensions, you start reaching close to 100%. So if you can imagine that we have an orange, the part that we can eat would be about 90% of the orange, and we have 10% of the volume in that orange peel. If you have the same thing and increase, for example, to 20 dimensions, then everything will be orange peel, and you will almost have nothing of orange inside. So when you're trying to separate your categories by looking at the frontiers and using distances to separate the parts that are in the core of each region, when you have many features, this no longer works very well, because almost everything is at the frontier, and so that's where things don't work. So this is the curse of dimensionality every time you use distance-based metrics for trying to classify, such as in k-nearest neighbors. And now let's see what we're going let's see an example of using the same principle of k-nearest neighbors, but for regression. So this is again an example of lazy learning. We are not trying to fit some model. We are just storing the points that we have, and then trying to predict values for new points looking at the closest neighbor. So in this case, we could use k-nearest neighbor regression with k equals 1. For each value of x, we look at the closest point that we have, and we predict that the epsilon value for this x would be the same. We have this discontinuous function here, but it follows all our points. We can increase the neighborhood. For example, this is the same thing but with k equals 11. This means that we're going to average we're going to look at the 11 closest neighbors, use the average value for those, and that would be our prediction. But note that this is always a discontinuous function, because as we are changing here in the x value, we often have the same neighbors, so it's the same value. And then one of the points changes, and we suddenly change the value abruptly. So we have this pair. We can control how smooth it is, but it always has this discontinuity. Okay. So k equals 1, k equals 11, k equals 15. We can do this however we want. The problem with this is that this is a stepwise function. As we change the set of points that are in the neighborhood, suddenly the value changes. We can smoothen this by using a kernel regression. So kernel regression is similar to k nearest neighbors, only instead of using only the k nearest neighbors, we are going to use all the points, but we're going to give less weight to the points that are farther away and more weight to the points that are close together to the value that we want to predict. And we're going to do that, use this scale, by using a kernel function. A kernel function is a function that is non-negative. It has an integral of 1 when you integrate everything, and it's symmetrical. It's the values above 0 are the same as those below 0. So the value of minus u is the same as the value of u in this function. Any function that fits these constraints can be used as a kernel function. Here are some examples. We can use a triangle, we can use a Gaussian function, cosine function, things like that. So anything that has these attributes, we can use as a kernel function. And this function will determine how much each point will weigh in our regression estimate. Then, let's see, for example, we're going to use a Gaussian kernel. This is a Gaussian function, which gives us that estimate for the weight. And now we have to aggregate the contributions of all the different points to get one prediction for a specific point. For that, we're going to use the estimator. For example, this is another Watson estimator, which is basically a weighted average of the epsilon values for all the points using the kernel function for different weights. So this is the kernel function based on the difference in the x values and multiplied by the epsilon value of each point. We are using this h value here to adjust how wide or narrow our kernel function will be. So this is a scaling factor or a scaling parameter that we can manipulate. But since we are multiplying the epsilon value of each point by this kernel function and then dividing by the sum of the kernel function values, this is actually a weighted average of the epsilon values of all the points in our data set, with points that are closer to the ones we want to predict having larger weight than the others. There are other estimators. For instance, Priestley-Chow for an equally spaced point has this weight that considers the distance in the x value between one point and the one immediately before that one in the series. This is useful for time series, for example, because if you have points that are very close together, then these points are do not weigh as much on the average. But if if there is a large gap in your time series, then this point will count more because you have less information. So depending on what kind of regression you're using, you may want to use different estimators, but the idea is always the same. You have this kernel function that smoothens the contribution of the different points depending on the distance, and then you have the estimator that aggregates all these contributions in a specific way depending on the purpose of the regression. So let's see, doing a kernel regression with a Gaussian kernel and another Watson estimator. This is simply the Gaussian function here, square root of pi and the e raised to the square of u minus divided by minus 2, and then the estimator, the another estimator here, which is simply the sum of the weighted contributions of all the points divided by the total of those weights. So with this two functions. You can implement, these are just the translation of those expressions. And now we can see what happens when we change that age value. So if you see here, the age parameter will scale the distance that we are counting when we are inputting the distance of the x values into the kernel. If we use a large h, we are scaling a small h, we are counting the distance as if it was larger. So actually we are scrunching the kernel together. We are using the kernel as if it was thinner because we are changing the scale on this x value. And if we do that, we are giving a lot more weight to the points that are nearby and rapidly diminishing the weight for the points that are further away. So if we do that and we effectively narrow the kernel, we get a curve that follows the points much closer. On the other hand, if we use a large h and we consider that all those distances as if they were smaller, then this effectively is working as if the Gaussian kernel was wider, and we are giving more weight to points that are more distant to the ones that we are predicting. So when the kernel is effectively wider, if we are predicting a value here, we are looking at points more distant to this one, and if we we decrease the value of h, we are narrowing that kernel, and we are looking only to the closer points. So this way we can adjust the regression. It's continuous all the time because this is a continuous kernel, but we can adjust it to fit more our training data or less. Once again, we can use cross-validation to determine the best value of h and get the best regression here. We can also use kernels for density estimation. This is a fancy name, but you probably all have done this because density estimation is what you do when you plot a histogram. Imagine that we have these data points here. This is only one-dimensional. We have more of them over here, less over here. They were drawn at random from a Gaussian distribution, so they have a higher concentration here. If we want to look at how they are distributed, we can do a histogram. For example, this green one here. We split into all these beans, we count how many points fall into each bean, and we plot the histogram. So the histogram represents the distribution. However, if we change the size of the beans, for instance in the yellow one, we get different counts and we get different shapes because points that would fall on one bean now fall on another, and some points are more bunched together in the same bean. So when you change the number of beans on the histogram, you can get very large changes and discontinuous changes because the size of the bars on the histogram are discrete counts of the number of points that fall into the bean. So the histogram changes discontinuously. If we want to avoid that, we can use kernel functions to smoothen the distribution. And the idea is simple. Imagine that you have these 5 points here, and instead of doing a histogram, let's say here it would be a bar of size 3, size 1, size 1, we can use a Gaussian kernel centered on each point, and then add the values for the kernel, the Gaussian kernel. So now we have, when we sum all these Gaussian curves, we have this smooth curve here showing us the distribution, and we can adjust the shape of the curve continuously by adjusting the width of those kernel functions. So depending on how broad or how narrow they are, the curve can change. So this is an unsupervised learning technique, but it's very simple and it's simple to understand once you look at kernel regression. And it's a very practical way of describing distributions of points or visualizing distributions of points without the problem that histograms often have. Also, you're going to use this on the first assignment. So next week I'm going to talk about the first assignment because you still need to learn about the naive-Bayes classifier. That's one of the classifiers you're going to use, and you're going to use also kernel density estimation for computing the probability distribution. So to do this, you can use the kernel density class in Python. You can create an object for doing kernel density estimation, which you can select the kernel. In this case, it's Gaussian. What will be the width of the Gaussian curve? And then you give it the data points so it can compute the prediction. Note that this is a lazy learner. It actually stores the data points, and then when we want to compute the value at some specific point, it will add all the kernel functions and give us the value. You can do that by using score sample, so you give the x values and ask for the score. Actually, the score sample gives us the logarithm of the kernel function. This is useful because typically kernel density estimation is used for probability distribution. And if you have to compute the joint probability of several probabilities, you have to multiply everything. But multiplying very small numbers has a problem with floating point underflow and so on. So actually what we do is to add the logarithms instead of multiplying the numbers. So typically these classes give you the logarithm of the values, because then you just sum everything to determine which is largest or smallest, whatever. To sum up, we saw this idea of lazy learning. We are not going to describe explicitly the hypothesis path with a model, and we are not going to try to fit the parameters of the model to get a hypothesis. We just store all the data, and then when we need to make a prediction, we look up the data that we have. K-nearest neighbors is a good example of that. We look at the k-nearest neighbors in our data set and make our prediction according to those values, and we can use that for classification and regression. We also saw a bit about this curse of dimensionality. Every time you want to separate two regions, you need to have some way of deciding where is the frontier and what are the regions. But as you increase dimensions, the frontier starts to cover a higher and higher percentage of the volume. So at some point, nearly everything is frontier, and things don't work very well. So when you're defining the regions by distance, or trying to draw some line to divide between two regions, you start having these problems. We saw how to use k-nearest neighbors for regression, but then we extend that and we use kernel functions for kernel regression and kernel density estimation to smoothen that way of weighting the different points and avoiding those discontinuities. So if you want to read more about this, you have Alpidin and Mitchell. Mitchell's book is a bit old, but talks about these, the basics a lot. Marsland's book is a bit more oriented towards code, so it may be easier if you take a look at the three and try to see which one is better for understanding this. So, and that's it for today. If you have any questions.